Hey there, guys. I'm Wiley Simpson from Axiom Materials. We're a company out in Santa Ana, California, and today I'm going to be talking about designing with CMC Prepreg, CMC Materials, some of the lines that we have. I'll probably wait a few seconds just to let a few people trickle in here, and then we'll get going. Let's see. All right, I'll begin. So again, I'm Wiley. I'm from Axiom Materials. We're a prepreg manufacturing company in Santa Ana, California. We're part of the Cordza family, and we have a load of products, and specifically the one that I'll be talking about today is our line of CMC prepregs. So today I'll talk through the summary of our company and a few of the composite materials we have, and then talk through some of the CMC materials we have to offer, and how you can build that into certain designs and the different properties this material system has as compared to other composite materials. Sorry, having some connection issues. There we go. Sorry about that. So I'll just talk through. So CMC Materials, reinforced ceramics. There we go. So we're Axiom Materials. We're a leader in specialty advanced composite solutions, part of the Cordza family. We have a 100,000 square foot facility down in Santa Ana, California, where we manufacture composite prepreg as well as some filament adhesives for end solutions that range from energy to aerospace to fishing equipment. We ourselves have a new high temp facility that focuses specifically on CMC prepreg. So we have a solution coating machine as well as a unidirectional coating line specifically for our CMC product line. Sorry about this. I'm just going to go to this mode. So CMC Materials, some of the ones that we focus on are in this area here. This is a good chart that tells you sort of the difference between the high temperature super alloys versus the CMC composites. Now CMC composites, typically they have a temperature application range from anywhere about 1,000 degrees Celsius up to around 2,700 degrees Celsius in the 6.6 CMC composites. And so this is a good chart to a selection to select your material. The difference between sort of the super alloys and the CMC materials is mainly just the lower density of these CMC composites versus that Inconel, which it saves you a lot of weight in the overall design of your component. Now CMCs are reinforced ceramic materials, and we do this to improve the fracture toughness as opposed to sort of monolithic composites or monolithic ceramics. These monolithic when you're thinking about ceramics as opposed to maybe metals, to improve that fracture toughness, you're looking to impede sort of crack propagation there, as opposed to dislocation motion in metals. So to do that, there are a few different ways to varying successes out there. You can add whiskers to sort of bridge those cracks. You can also there's toughening mechanisms through phase transformation toughening, like that zirconia toughened alumina. But we do sort of the more common and the more successful version of that, which would be to reinforce that monolithic with fibers. Ceramic fibers specifically, to bridge those cracks, to deflect them, to impede their movement through the ceramic material, and that's what we do. So there's a few different versions of the CMC prepreg that we have to offer that I'll talk through later or right now. So we have a few different systems that vary on the matrix as well as the fiber, and these are all tailored sort of to your max operating temperature, as well as the structural properties that you're looking for. Yeah, so here's just a quick list that I'll talk through in more specifics on the next few slides. So there's the 610, the 720, and the 312 fibers offered from 3M, and we have different solutions to matrices to coat them with. The 610 all alumina fiber is the more structural grade component, and this is structural at room temperature. When it goes up to high temperature for long continuous use, the 720 is more preferable due to its creep resistance, and then the 312 is sort of the lower cost grade ceramic, which has a few unique properties to its system that I'll discuss. So CMC production follows sort of the same routes that composite production does. Composite prepreg. You have a fabric, you coat it with our solution, lay it up, autoclave cure is what we'd recommend, and then sinter it at high temperatures. That's the one difference between sort of processing those standard polymer matrix composites versus these high temperature CMCs. There's a sintering step that's required after autoclave cure. So here's some of the typical properties we see from our CMC prepreg. The naming system up here, AF stands for is the 312 material. EF, if it starts with an E, that's the 720 material, the highest temp grade material, and then DF, that's the 610 grade stuff. And they offer a bunch of different fabric architectures and different weave styles. So different deniers, different weaves, and that allows you to sort of tailor your per ply thickness for your design, end of life design component. So there's a various degree of per ply thicknesses that we offer. Seen here, the higher the number up here, typically the higher the per ply thickness. Fiber volume for this stuff is typically around 42 to 50%. Matrix of volume around 30, and porosity, you're going to see a porosity of around 20%. Now that porosity is essential in a system like this ox-ox system, because it creates that it allows those sort of weak fiber matrix bonds to form, which are essential in deflecting and impeding crack growth through the system. So that's why 20% porosity is sort of inherent to the system and necessary for it not to become brittle. Sorry about these struggles. Hope everyone's having a good conference. Here we go. So in talking about some of the mechanical properties here, you're going to see difference between each kind of types of fibers in these ox-ox systems. As I stated earlier, the 610 system is going to have the highest structural grade, whereas the 312 is going to have the lowest. But the 720 at those high temperatures, at around use temperatures of 2000 degrees Fahrenheit, you're going to see that the 610 and the 720 start to even out because of the sort of resistance to creep that 720 fiber has, that aluminum mullite fiber, and that aluminum mullite fiber has a sort of a creep resistance mechanism in its grain structure. Sort of grain pinning allows it allows those grains not to grow so large that they're weakening the matrix or the fiber at those high temperatures. Sorry about this. So yeah, as I was saying, you're gonna see a pretty huge difference. Hopefully, I can show it in a second. Just having connection troubles over here. But anyway, you're going to see a huge difference between the shear properties as well as the flex properties and the tensile properties of these materials at room temperature. And then when you escalate to that high temperature, the 720 and the 610 systems are going to sort of have the same properties there due to that creep resistance of the 720 fibers. Man. Let's see. Sorry about this, guys, again. This is why you don't have presentations on online on these. Here we go. So you can see some of the properties of the short beam shear properties and the difference, the stark difference between the Nextel fiber types. I may have talked a little bit quickly through that, but there are those three different Nextel fibers: the 610, which is all alumina, the 720 aluminum mullite, and the 312, which is more the mullite brand. So here you can see the short beam shear strength as well as the flex strength, a bunch of stark differences between the fiber systems, where the peak temperature is around, or the peak flexural strength is around 330 millipascals, and the 312 has more around that 74 millipascals, or sorry, megapascals. So here's those properties, tensile properties at temperature. You can see here, as that temperature gets to around 1,000 to 1,100 degrees Celsius, the 610 properties start to lower a little bit, whereas the 720 has more strength retention at those temperatures due to those, reduced grain boundary slipping in 720 fiber. Here's a study we did on sort of room temperature tensile strength retention on the 610 fiber after numerous cycles at various degrees. You can see here 900 degrees Celsius. The temperatures stay, or the mechanical properties stay pretty consistent over a 500-hour cycle at that temperature. Then when you get to around 1,100 degrees Celsius, for long periods of time, that 610 fiber starts to creep, and those tensile properties start to lessen after long periods of time. Another interesting difference between the CMC components is the sort of dielectric properties in difference between them. The 312 fiber, which is the low-cost one, actually has a very low dielectric constant, and for that reason, it's typically used in radome applications, in applications where you want to send a signal through without losing too much of it at those high temperatures. So here's the difference: 610, the all alumina. So standard alumina has typically a dielectric constant around 10, whereas silica has it around 4. So that's why you're kind of seeing the difference in those dielectric constants, with the all alumina fiber having the highest and the more mullite fiber having the lowest, and the aluminum mullite somewhere in the middle here with the 720. Another product that we have to offer that's pretty unique is a CMC surfacing film called Surface, and this is meant to co-cure to the surface of these ceramics to reduce surface roughness as well as reduce surface porosity and create more cosmetic finish. You can see here difference between the surface roughness of prepreg with it and prepreg without it, and the stark difference you're seeing between those two systems. So this is something that you'd cure to the surface of a component, maybe be the first layer you lay down on your tool to really add some of that smoothness to your component. It also fills in some of the pores at that surface to help in maybe corrosion resistance or other penetration issues that happen with CMCs. I'll talk through some of the applications there are for this material. One would be in the aerospace division, hot aero engine components, typically static components like the static mixer or heat shield shrouds, nozzles, tail cones, anything that sees high temperature that doesn't see too much load, not too much of a load-bearing component. And these are good for these applications because of their high temperature capability as well as their weight. They're 1/3 the weight of nickel super alloys. So they allow your engine to sort of run hotter and run lighter, reducing emissions and noise, increasing engine efficiency and decreasing fuel consumption. One thing about this material too is we've done a public NIAR FAA study, and we'll be publishing some of the static properties of that material in CMED 17 in the coming year. Another application we've found for this type of material is in high temperature refineries, in places that see are high corrosive environments that need an inert material that can handle high temperatures. And this is good also because it has a lot of oxidation and abrasion resistance. The OXOX system is unable to oxidize at those high temperatures, as opposed to sort of non-oxide systems. And it's fairly abrasion resistance with high operating temperatures. Same thing with refinery systems, places that are caustic and corrosive environments that need maybe a little more structural strength, components that tend to break often, where you need to put down your furnace line and in burners and whatnot. These are materials that can extend the life of your system in ways by maintaining structural integrity at those high temperatures. Another application, radomes, which I spoke briefly on before, and this is because this is typically with a 312 system, and this is due to the low dielectrics and the high temperature applications of this material. So that's why it's a common material used in those radome systems. Let's see. I'll keep in non-presenter mode. Anyway, so to summarize kind of some of the stuff, I may have talked through it a little quickly, and sorry about the presentation issues I'm having here. But ceramic matrix composites, we spoke about this just to sort of get it out there, get some of the unique properties that this material system has to offer. And that is thermal shock resistance, low density, high temperature fracture toughness, which is one of the keys that differentiates it from monolithic ceramics. It has, it's a unique material, and then it's ceramics in general. They're inert, so they're typically corrosion resistant, and there are ways through additions of different material systems, through densification, to make it even more corrosion resistance for those environments with high slag or other. They have low CTEs, low thermal conductivities, and so they're great insulating materials. So we offer a variation in matrix, fiber, and fabric architectures to allow for flexibility in tailoring prepreg systems for unique applications. And some of those target applications we spoke about are aero engines, refractories, refinery piping, fuel cells, radomes. Another few things I'd like to drop in are some of the new products we're developing, and that's unidirectional aux prepreg for advanced fiber placement and automated tape layup applications. These are great because you can make really simple large components quickly, cost effectively, and a great system for aero engine applications. We're also developing a 6-sig prepreg system for extremely high temperatures, that 2,700 degrees Fahrenheit, with higher structural yield, as well as an aux bulk molding compound which can be used somewhat as an adhesive between components, CMC components. So here's how you contact us and our business website. I'm Wiley again, ceramics engineer. A few of our other colleagues, Antonios, Greg, and Raj, there's their emails, who also work on the CMC systems. So again, sorry for the presentation issues, but thanks for joining us. I guess we'll open it up to any questions. If you have any questions, maybe in the public chat down there. Infusion technologies. Sorry, I'm not too familiar with that. So the 6-6 system will be in a prepreg form. With the high nickel on fiber coated with a SIC resin system. Application for automotive field. Yeah, so automotive field, that would be maybe an EV, the EV battery systems right now, as sort of a thermal shield for those EV battery systems to protect from thermal runaway, and that would be one application for in that automotive field, sort of a battery enclosure for lithium-ion batteries in case they go into thermal runaway, to sort of insulate that. Reason for sintering at the end of the process, that is to sort of densify the material and really create those, that at high temperature, that's where these bonds are really sintering together, forming together. So that's why you sinter at the end of the process to to make that matrix a little tougher there. Simulations needs of Axiom in order to predict the behavior of innovative materials. Yeah, so we don't have any simulation systems. We're just typically stick to material processing and not really design of these materials. We just help in our customers in providing material processing guidelines and other 6.6 prepreg. That's processed in somewhat a similar way to the OXOX CMCs in that first procedure, but it requires even higher temp sintering furnace and sort of a PIP processing, a pyrolysis infiltration processing, steps where you sinter at those high temperatures. It may lose density because of some of the stuff burns off, and then you re-infiltrate it with more resin and then fire it again to make that system extremely dense. The silicon carbide needs to be a really, really dense system at the end of stuff. So it follows some of the same procedures, but in the end, the sintering procedure is maybe takes a lot of re-infiltration and pyrolysis to really get that thing nice and dense. Appreciate it. Great. So yeah, appreciate you guys attending this thing. Any questions? You can go to axiommaterials.com. My email is wsimpson@axiommaterials.com. And be great to hear from you. Thank you guys.